Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at a problem from UNSW on thermodynamics. This is a bigger problem. It's still, tackling the basics, but it's a bigger problem that requires us to do for every single state, understand what's going on, relate the first law of thermodynamics, and the ideal gas law. So it's a very complete problem, yet simple, so it's a good exercise to learn these concepts. Problem statement reads like so. 1 kilogram of air in a closed system initially at 27 degrees Celsius and 200 kilopascals receives 120 kilojoules of heat at constant volume. The system then undergoes a constant pressure process such that the final temperature of air is 50 degrees Celsius. Show the process on a PV diagram, given the values of P, V, and T in each state. Find the total work and the heat transfer during these processes. Note that C sub V of air is 0.718 kilojoules per kilograms per Kelvin. And then we have some of the answers there. Okay, so let's analyze this bit by bit. We're dealing with 1 kilogram. That's good. We are initially at 27 Celsius. Note that we have Celsius here, but we're going to be dealing most likely with C sub V, which is dealing with Kelvin. So we're going to convert that. One of the first things we're going to do. It receives 120 kilojoules of heat at a constant volume. So whenever we hear or see constant volume, already be thinking there's no change in volume, therefore there's no work, right? So therefore this means that the whatever change in internal energy that occurs in this system is going to be equal to the heat. The other thing to note here is that this is a closed system, and this is just telling you are welcome to use the first law on that way that you have been taught, which is delta U equals Q and work. Okay, so it's a closed system. Whatever is happening to this system has to respect this. The system then undergoes a constant pressure process. So then we have a constant pressure process, which whenever you hear or read, you need to be thinking to yourself, okay, if it's a constant pressure process, that means that when I do the integration for work, pressure comes out of the integral, so it's just pressure times the difference in volume. So it's an easy way to find work. And the final temperature of air is 50 Celsius. So once again, we have Celsius there that I want to convert into Kelvin. We want to show the process on a PV diagram, and we want to give the values of pressure, volume, and temperature for each, and also the total work and the heat transfer. So there's a lot going on here. They're wanting us to find T1, T2, T3, volume 1, volume 2, volume 3, pressure 1, pressure 2, and pressure 3, and finally work total and heat total. Okay, so a lot of things we need to find. Obviously, some of these things we already know from the start, like T1 has been given, right, 27 Celsius, and T3 has been given 50 Celsius. Pressure 1 has been given. So let's go ahead and eliminate those. So T1, T3, pressure 1. What else? I think that's it. That's all we have. Okay, we need to base everything off that. Okay, so what I'm going to do is I'm going to go ahead and put a little energy diagram of those that we do. Just energy here, and I'm going to say that state 1 is down here, and I know that state 2 is, call it up here. Okay, so we're going from a state of we're receiving 120 kilojoules, so therefore I know that my internal energy needs to increase, right, as we go from state 1 to state 2. Now, for state 3, I'm not sure. We only know the temperature so far. I don't know if state 3 is over here. That is higher energy than state 2. If it's down here, that is, state 3. If it's down here, that is in between state 1 and 2, or if it's down here, that is lower than state 1, okay? And we need to do some detective work to be able to find this out, and then we can eliminate as we go so that we can understand what's going on. So the other thing we know that there's no work as we go from 1 to 2, right? So this has to be heat being given, right? So the 120 kilojoules is heat. That is therefore increasing my internal energy. Okay, what else do we know? We know that pressure 1 is 200 kilopascals. We know that temperature 1 is 27 Celsius, which is the same thing as 300 Kelvin, right? So I'm just summing 273. And the same thing for T3. I know it's 50, so that's going to be 323 Kelvin. That's what I know so far. So because the temperature is higher from T1 to T3, I don't think that will be the case. All right, I'm going to be sure as we go, but I don't think that will be the case. It's probably going to be one of these two. All right, so the first thing I'm going to do is let's go ahead and find the volume for state 1, because I have two properties. I can just find the volume easily. All right, and this problem, the way we're going to solve it is basically using ideal gas law and C sub V and first law. Those are the three things we're going to be using to solve this problem. That's all we need. Let me put it down here so that if you don't want to watch this video anymore, you can just grab this and run. All right, so pressure times volume equals mass RT. You can use this, or you can use number of moles as N here. That's fine. Then you're going to use first law of thermodynamics, and the other thing you're going to use is the definition that C sub V is the way that my internal energy varies with temperature. That's all you need to do to solve this problem. All right. So I'm going to start with this guy to find out what is my volume, because I know the pressure and the temperature, but I don't know the volume just yet. So that means that pressure 1 times volume 1 needs to be equal to mRT1. Okay. Now you can go and find out what is the R for air. Okay, R for air. In the tables, in the thermodynamic tables, or you can go ahead and use the universal R, right? So you do universal R, universal gas constant. That will allow you to use this equation too. It's up to you, whatever rocks your boat. Okay, so I'm looking for V1. I'm looking for V1, so that's just going to be M or N R T1 divided by pressure 1. Okay, so in this case here, if I'm using moles, I'm going to convert 1 kilograms to moles. If I want to use the kilogram one, I need to grab the R for gas, and in this case here, R for air is 0.287, and that is kilojoules per kilograms Kelvin. Okay, again, just the difference between these two is whether you're using the universal one with moles, or if you're using the specific one for air, which is in kilograms. All right, cool. So let's do, this is 1 kilogram that we have of air. This is 0.87. This is 300 Kelvin, and we're dividing the whole thing by 200 kilopascals. So let's check on the units, but we should be good. All right, I'm going to put the units down in a second. This gave me 4305. And then the unit here, let's check. We have kilograms. Then we have kilojoules per kilograms per Kelvin. Then we have 300 Kelvin. In the bottom here, we have kilopascals. So kilograms and kilograms, Kelvin and Kelvin. Kilojoules and kilopascals, the kilo go away, and we're left with joules over pascals. Joules over pascals. So that's not going to help me. I need to convert this joule into something else, right? So I know a joule is unit of energy, and I know energy is defined as force over a distance, or pressure over a volume, right? Which is actually equivalent. And what I can do is transform a joule into a meter cubed times a pascal, pressure times volume. So therefore, this becomes meters cubed pascals, and then pascals and pascals are left with meters cubed, which is super convenient because we're looking for volume. All right, so we got the first one out of the way, which is this guy here. All right, next up, how can we go to state 2? Well, we know the C sub V. All right, so what do we know for state 2 as we go from state 1 to state 2? We know there's no change in volume, so we know that volume 1 equals volume 2. So wait, we already know that, so brilliant. So this is the case, then we know this guy too. What else? We know that C sub V equals du dt. over here, and you can check out on the previous video we talked about when you can use the simplification of using constant 1. In this problem, this is the case. So we can say C sub v delta t equals delta u. All right, we have this, we have this, we have one of the temperatures. So we can solve this for the state 2 temperature. Okay, note that we can do that only because delta u equals q and work. But work is 0 because there's no change in volume as we go from 1 to 2, right? So as we go from 1 to 2, there's no change in volume. So therefore, delta u equals q. And q is 120 kilojoules from the problem statement. Okay? So because of all this, now here we can go and combine these two pieces of information into the idea at 0.7, what was it? 0.718 times T2 minus T1, T1 is 300, has to be equal to 120 kilojoules, all right? And we're going to check units in just a second. So this means that T2 will be 300 plus the 120 divided by the 0.718. Okay, and this happens to be 467.13 Kelvin. All right, now let's look for units. We have Kelvin, here we have kilojoules, and we're dividing the kilojoules by kilojoules per kilograms Kelvin. All right, so we have a problem here. Oops, we want it to be in Kelvin. Kilojoules. So we have over here, what we actually have is kilograms times Kelvin. Okay, so we don't have the units right. So that means we need to put I'm going to go back one step, and we're going to see that over here, I need to be multiplying it by the mass. Luckily for us, the mass is 1, right? So I'm going to multiply this by 1. So this is not going to change any numbers, but then look what happens with the units here. We have kilograms multiplying kilojoules per kilograms per Kelvin, okay? And then multiplying that by kilograms or by Kelvin over here, and that has to be equal to kilojoules. So kilograms and kilograms, Kelvin and Kelvin, and then we're left kilojoules. All right, so that works out well. So what I can do is, obviously, I can leave the temperature here and then send everything else dividing. So this is going to be kilojoules on the bottom here, kilograms over here, Kelvin over here, and then kilograms over here. So kilojoules, and then Kelvin equals Kelvin, which is what we're looking for. All right, so luckily for us, nothing changed, but we would have the 1 of the mass multiplying both these guys here. All right, beautiful. So this is temperature 2, which is one of the things we're looking for. Where's my temperature 2 in our little thing? Okay, cool. So we got all the temperatures. We got volume 1, volume 2. Now we need to go to the third one. So we know it's a constant pressure process as we go from 2 to 3. So if you can find the pressure on 2, we can eliminate 2 of the unknowns. And that's relatively easy because we know that P2V2 equals mRT2. So therefore, if I want my pressure, all I need to do is my 1 kilogram times my 0.287 for the gas constant times my 467.13 divided by the volume that I've always known because it's the same as state 1, and that is, what was it? 0.4. I lost it. Where is it? 0.4305. Okay, so we check the units on this. We should be good to go. Pressure 2 turns out to be 311.42 kilopascals. All right, obviously you're free to check this unit-wise, and you actually should check this unit-wise so that in case I did any mistakes, you can correct me, but we should be good here. Okay, and then state 3, we know that state